Hello, my name is Zachary Turner, and this is a presentation on electron density variations affecting radio frequency attenuation. For some background information about how electron densities can affect the attenuation of an electromagnetic wave, the total electron content is the total number of electrons accumulated along a transmission path as they penetrate the ionosphere. For the total electron density, it's given by an equation here, where N max is equal to the peak electron density at a maximum height. H is the height, Hm or H max is the height of the peak electron density, and capital H is the scale height, which is the height of the ionospheric region. For the total electron content, this is given by an integral from one height to another of the total electron density. These variations are caused by solar activity, geomagnetic storms, and terrestrial gamma ray flashes. Traditionally understood, the higher frequencies are more susceptible to attenuation due to their increased interactions with atmospheric molecules. Radio wave propagation will be severely impacted in an environment with a high electron density. One example of this is the atmospheric reentry demonstrator, which experienced a complete communication blackout from 90 kilometers to 50 kilometers, lasting about 5 minutes. The plasma frequency, represented by Fp equals 1 over 2 pi, times the square root of an electron point charge squared times the total electron density divided by electron mass times the permittivity of free space. This plasma frequency will equal 9 times the square root of the total electron density. Looking at some of these numbers, if we started with the plasma frequency formula and a total electron density of 2 times 10 to the 16th, which is very high, following the math, we'll see that the plasma frequency will equal 1.273 gigahertz. As we relate back to the atmospheric reentry demonstrator, if the frequency of the electromagnetic wave is not higher than the plasma frequency, then the wave will not be able to penetrate and travel outside the plasma. You can see here the frequency, if it was 3 gigahertz, that would be greater than the frequency of the plasma, which means the wave would be able to escape. Some solar events that cause these electron density variations are coronal mass ejections, where plasma is ejected from the solar cornea, sudden ionospheric disturbances, where X-rays produced by solar flares strip electrons from other atoms in the atmosphere. This can include oxygen, molecular oxygen, nitrogen, molecular nitrogen, hydrogen, and helium. The Sun experiences an 11-year cycle of increased sunspots, solar flares, and CMEs, where the expected maximum of the cycle is July 2025. The current cycle we are in began in 2019 and is expected to end in 2030. Here are a couple different types of attenuation. We have absorption, multipath, beam spreading, diffraction, scintillation, free space loss, reflection, refraction, scattering, and Faraday's rotation. All of these different forms of attenuation will affect electromagnetic waves in different ways. The one we will cover for electron density variations will be Faraday's rotation. So as we kind of talked about, Faraday's rotation is caused by when a linearly polarized wave is traveling through a medium of free electrons. These free electrons are then subject to the Earth's magnetic field, where it will rotate the wave's polarization. If we took an antenna designed for a vertical polarization and it now had to receive a horizontal polarization, this antenna would be unable to fully receive that signal. This will cause weaker returns or full communication blackouts. This Faraday's rotation is given by a formula where it's measured in radians of rotation. Factoring in the integral of the magnetic field will determine the overall rotation of the polarization. If you had a stronger magnetic field, there will be greater rotation prevalent on the electromagnetic wave. A terrestrial gamma ray flash, or sometimes known as dark lightning, is a brief burst of high-energy gamma radiation caused by thunderstorms. These TGFs can cause a relativistic runaway electron avalanche, where the electrons experience an electric field strong enough to accelerate them faster than they can be stopped by an atmospheric collision. These high-energy electrons collide with air molecules, knocking out secondary electrons. These secondary electrons are also accelerating, which creates the avalanche effect of runaway electrons. This process from TGFs and runaway electrons creates a self-sustaining and exponentially increasing electron population. Here we have the total electron density profile, where the burst region is represented by the red dashed line, and the blue line represents the profile of an electron density. This is measured by the Kp index, which is the Global Geomagnetic Activity Index. And as we can see, as we get closer to the burst region, the electron density increases. If we were very close, roughly 10 kilometers away from it in altitude, the electron density would be 1.9 times 10 to the 14th. But if we were further away, say 200 kilometers, we would notice the electron density would roughly be 12 times 10 to the 12th. These TGFs can affect a large area, as some have even been recorded to be observed up to 500 kilometers away from the original TGF. These graphs here show the total signal attenuation compared to a 9 gigahertz signal to a 30 megahertz signal around a terrestrial gamma ray flash. Immediately, we can see spikes in attenuation very close to the region of the TGF, where the altitude was 70 to 90 kilometers. The big difference between the 30 megahertz versus the 9 gigahertz is the total attenuation. We can see the attenuation in decibels per kilometer is an average of 1,000 compared to roughly 0.1 for a 9 gigahertz radar. We are now going to take a look at how different frequencies of electromagnetic wave will attenuate differently in a quiet versus storm condition. The quiet conditions represents a Kp index of 2, and the storm conditions represents a Kp index of 7. Attenuation will be on the y-axis and altitude is on the x-axis. Altitude will be measured in kilometers. As we can see, the attenuation of a 9 gigahertz radar at an altitude of 100 kilometers is just over 2 times 10 to the negative third. Overall, that's not a lot of attenuation, and we'll see that as we look at some of these other frequencies. Here we are now looking at a 3 gigahertz radar, comparing the same quiet and storm conditions. Immediately, we'll notice a general trend in the attenuation as it's increasing with a lower frequency. The attenuation is still roughly doubling compared to a quiet versus a storm condition. As we now move into a standard VUHF frequency of 300 megahertz, we'll notice the attenuation is significantly increased to those of a 3 gigahertz or a 9 gigahertz radar. The same quiet and storm conditions apply here, where now the attenuation in a storm condition is just under 2 decibels per kilometer. This is significantly higher than those of a 3 gigahertz or 9 gigahertz radar. And finally, for our data, we have a HF frequency of 30 megahertz. This attenuation in the high frequency range is significantly higher than those of 300 megahertz, 3 gigahertz, or 9 gigahertz. The same conditions apply between storm and quiet. However, in a storm condition for a high frequency wave, we're looking at roughly 180 decibels per kilometer of attenuation. Here we have some final results as well as an electron density profile graph showing the electron density on the y-axis and the altitude in the x-axis. Again, we're comparing the same quiet and stormy conditions, whereas quiet is a Kp of 2 and the storm conditions is a Kp of 7. One thing to note, the total electron density is roughly double a quiet versus a storm, where a storm is just under 3 times 10 to the 14th, and the quiet condition electron density is roughly 1.5 times 10 to the 14th. Looking at this graph compared to our attenuation graphs, we see a same general trend in the slope of the two different lines. Overall, our results have shown us that an increased total electron content will affect a radio wave's attenuation. Waves of a lower frequency are significantly worsened by their performance due to the total electron content. Effects could include communication blackouts, ambiguity of radar signal returns, or GPS SATCOM time delays depending on the form of attenuation and the content of the electron density. Finally, to wrap this presentation up, here are some of our references used during this project. If you made it this far in the presentation, thank you for joining me, and I hope you got the opportunity to learn something new about how electron density variations can affect radio frequency attenuation. Have a great day.